Okay, so the other day we talked about arithmetic sequences, which were linear. They had a common difference. So an arithmetic sequence we learned had a common difference, which we use the variable d to represent in our formula, and that they were linear. The other type of sequences that we're going to look at are geometric sequences. Geometric sequences have a common ratio, which we use the variable r to represent, where instead of being linear, they're exponential. Okay, so those graphs are going to grow or decay, like our exponential functions earlier this unit. So we have defined our arithmetic sequence on the notes before. Defining a geometric sequence is that each term can be found by multiplying the previous term by a common ratio, which we call R. Okay, common ratio versus common difference. So we want to be able to also determine if the sequence we're looking at is geometric or arithmetic. So you'll see that in some of the work that we'll do for sequences and also in our unit review. So when I'm given a sequence, even if I'm not told if it's geometric or arithmetic, I know what the difference between them is that for one, I'm adding the same amount, and for another, I'm multiplying the same each time. And so looking at this, I could say, okay, that's 9. Okay, that's definitely not just adding 9. This is times 4 again. So I can determine, even without it telling me, what type of sequence I'm looking at. So I can see it's geometric, and I can see that the ratio is 4, that each time I'm multiplying by 4 to get the next term. So it asks me to find the next 2 terms in that sequence. So that means I'm going to take 48 and I'll multiply that by 4, which is 192. And then I need to multiply by 4 again to get the next term, which gives me 768. Okay. So you can see it grows much faster, right? A geometric sequence, just like our exponential function, it's going to increase at that faster rate. That's that exponential growth. You could also have exponential decay, or like that a geometric sequence that would model exponential decay, and that would mean our ratio was a fraction. So I take a half each time or a third each time, and that's what the ratio is. That's what I'm multiplying by. Okay. So let's kind of discover what formula would work here. And we're going to look at the geometric sequences 2 different ways. So I'm going to list the sequence that's above: 3, 12, 48, and 192, and I'll just leave it there. Okay, that's good. Now the notation is the same. So you would think that, or I've heard students say before, like, well, why are they both A? That's just the sequence notation. That's the notation we use. So the A had nothing to do with the fact that it was an arithmetic sequence the other day when we were talking about it. We still call our first term A sub 1, our second term A sub 2, our third term A sub 3, and our fourth term A sub 4, and then so on, and we could find the nth term of a sequence. We're now going to take this sequence and we're going to write it again, but we're going to write it in terms of R and the previous term. So for the first one, it's just 3. There's no term before it. We're just writing, okay, our first term is 3. Then we want to write, so R, we know R equals 4 in this sequence. So we want to write 12 in terms of the term before it and our ratio 4. So we would write 12 as 3 times 4. If we wanted to write 48 in terms of our ratio and the term before it, here's our ratio, we'd have 12 times 4. 192 is 48 times 4. Okay, so we can write our number using the term before it and our ratio. If I were to use the notation here to write that, then I would say that I have A sub 1 times my ratio. And then I have, this is my second term here, times my ratio. 48 is my third term, and 4 is my ratio, okay, and so on. And what you might notice is that for 192, which is the fourth term, I'm using the third term, right, term before it in my ratio. For the third term, I need to use the second term times my ratio. So in general notation, we can say I didn't need the parenthesis there, n minus 1 times r. Okay, that whatever the term before it times my ratio is going to give me that number term. So if I wanted the 50th term, I'd have to know the 49th term, and then I'd multiply it by 4 to get that 50th term with it written this way. Now, I'm not always going to know the term before it. So we want another way to look at these sequences. So now we're going to express it in terms of the ratio again, which is 4, and just using the first term. Okay, so my first one is 3. So if I were to take 3 and multiply it by my ratio, we have 4 to the 0, or just 3 times 1 is what that would be there. If I want to write 12 in terms of the first term and my ratio, well, first term ratio 12 is 3 times 4. So it's 3 times 4 to the first. If I want to write 48 in terms of my first term in my ratio, now what I'm going to do is I'll have 4 squared, or 16 times my first term of 3. And you may be able to guess that to express 193 in terms of the first term in my ratio, I have 4 cubed times my first term of 3. And so using our notation, this is just my first term, right? This was my first term times my ratio to the first power. This was my first term times my ratio to the second power. First term times my ratio to the third power. And in fact, we can find any term by taking the first term and multiplying it by the ratio to the n minus 1 power. Okay. So we have 2 formulas that we look at for geometric sequences. This one is called the recursive formula. I need the term before it, need the previous term. This is called the explicit formula. Explicit meaning I don't need the term before it. I can just direct substitution whatever n is into my equation and be able to use it to find that number term. We really like this formula better. Okay, we're going to look at both for a moment, but overall we kind of stick to this one because it doesn't rely on us needing the term before it. So when you're ready, flip this page. And let's rewrite our explicit formula. So to find the nth term, we take our first term times our ratio to the n minus 1 power. There's our explicit formula for geometric sequences, where a sub n is the nth term, a sub 1 is the first term. This is our ratio, and n is whatever term number we want to find. Okay. So let's look at both methods. First, looking at the recursive and the explicit formulas. So recursive, using the term before it, our recursive formula was that to find the nth term, we took the term before it and multiplied it by our ratio. The explicit formula is we need to know the first term, and then we multiply that by our ratio to the n minus 1 power. Our recursive formula we kind of use for this sort of thing where it says find the first 6 terms. We don't really think about it as a formula at all, but it tells us our first term is 3 and our ratio is 2. So if our first term is 3, then our second term times 2 there would be 6. And our third term, if we multiplied by 2 again, would be 12. And our fourth term, if we multiplied by 2 again, would be 24. And our fifth term would be 48. And our sixth term multiplying by 2 would be 96. So when we want to list whatever the first 6 terms, the first whatever terms, recursive makes sense where I list a term, then I just keep multiplying it by my ratio, take that term, multiply it, take that term, multiply it, and I get my list. For my explicit formula, I don't need the term before. So that means I could have gone from my first term of 3, and if it asked me just to find the 6th term, it's a lot easier to use the explicit formula, where I know the 6th term is 3 times my ratio, which we're told is 2, to the n minus 1 power, n minus 1, 6 minus 1 would be to 2 to the 5th power. And then you'll have access to calculators for this work. And we do 3 times 2 to the 5th power, and we get right to 96. And I didn't need all the terms in between. I can go right from term 1 to term 6 to term 600, doesn't really matter. I can keep using my explicit formula to find any term number there. Okay, so that's where this one's really nice to have, to jump to any term. Recursive is more nice if I just want to create more of a list. Okay. So for the next problem, it says find the 9th term of the geometric sequence. Method 1 doesn't help us very much because I don't want to have to list 9 more terms. Although it does, this one is the first one that's a little different because it gives us the 3rd term in the sequence. You see that it gives us the 3rd term. And my ratio is -3. So we're going to have to do some problem solving there. But if I wanted to find the 9th term, I'd have to go, well, the 3rd term is 63. And so I need to find, I need to find the 4th term and the 5th term and the 6th term and the 7th term and the 8th term before I can even find the 9th term, because recursive, again, I have to rely on the one right before it. So I don't even want to look at method 1. I'm going to go and look at method 2. Now, here's the issue is that we don't have the first term. So there's a few ways that I could do this. I could work backwards, like I could divide backwards. So if I know my rate is -3, if I know the 3rd term is 63, I could divide, instead of multiplying, I could divide by -3. That gives me my 2nd term. And I could divide by -3, making it +7. That would give me my 1st term. That's probably the easiest way to do it, unless it gives you like the 70th term. Then I wouldn't want to work backwards that way. Okay, but here's my 1st term, which I'm going to need, and here's my rate. You could also do that using our equation. You could have also found the 1st term using our equation. So here's our explicit equation for geometric series. And if I have the 3rd term is 63, a sub 3 is going to equal a sub 1 times my rate, which is -3 to the 2nd power, okay, because it's going to be 3 minus 1 here. Well, I know that a sub 3 is 63. So another way that I could have found my 1st term is plug in the 3rd term, my ratio to 3 minus 1 power. And now I'm just, okay, so 63 equals a sub 1 times -3 squared is 9. And I divide by 9. And I get 7 for my 1st term. Okay, so this one is trickier because it does not provide me with the 1st term. But I'm showing you 2 different ways I could have found my 1st term, using the formula or working backwards. Now I still haven't answered the question, which is what's the 9th term? So to find the 9th term, now that I know the 1st term is 7, I'll plug 7 in, times my rate is -3. To the, if it's, I want to find the 9th term, I want my exponent to be 1 less than the number term I'm finding. So I'm going to have -3 to the 8th power, 9 minus 1. And I'm just going to use my calculator for this. So I'll have -3 to the 8th power times 7. I could have typed it all in to the same line as well. Be careful with negatives. Make sure you put them in parentheses in your calculator before raising them to whatever exponent power, because it can mess up positive and negative if you don't do that. Like this is an even number exponent. Even number of negatives gives me that positive answer there. So I get 45,927 would be the 9th term of that sequence. Okay, it started at 7, and in 9 terms it grew to be 45,000 something. So you can see how the explicit formula is a lot nicer, because I don't have to like have those large numbers and keep multiplying and multiplying and multiplying until I get to here. Okay, so you'll have some work that mixes geometric and arithmetic sequences together. And so part of your kind of challenge with that is being able to differentiate, given a sequence, is it a common difference or is it a common ratio?